All right, everybody, welcome to Math with Grace. Today we're going to be working through Geometry Book 1009, Section 1, Ordered Pairs. We're going to start out with a brief discussion about points in a plane, specifically the coordinate axis. The coordinate axis is broken up into 4 different planes or regions called quadrants. Now, this should all be review for you guys. We've talked about this similar things before, but the quadrants, I'm going to go ahead and label them. This is the first quadrant, second, third, and the fourth quadrant. Okay, this center point is called the origin, the origin point, and it is at 0, 0. The x-axis is our horizontal line, and the y-axis is our vertical line. And them put together, the x and the y-axis together, is called the coordinate axis or the coordinate plane. All right, and like I said, the origin point is at 0, 0. If we take a look at this coordinate plane or coordinate axis that I have drawn here, I've taken it from Model 1 on page 3 of your book. And we have our plane, and then they've listed a set of points that they want us to locate on the plane. When we look at our sets of points, our set of ordered pairs, it is always written x, y. That means the number in the first part is considered on the x-axis, and the second number then is the y-axis, and that is how we're going to plot our points. So if we look here at point A, it is at 2, 4. The 2, like I said, represents the x-axis. So we're going to go over a positive 2. And the 4 is representative of the y-axis, which means we're going to go up a positive 4. And where those 2 points meet, a positive 2 on the x and a positive 4 on the y, that is where our point falls. Okay, so point A is at positive 2, positive 4. Now, you can use graph paper. It's probably a little bit easier to see the grid, or you can, in the book, the homework examples all have small graphs for you to work with, so those will be there for you. Feel free to label your points if you want, but really you only need to label them if each mark represents more than one block. Otherwise, it's understood that each mark is one block, okay? Next, point B. Point B is at negative 3x, positive 7 on the y. So we're going to come over to our negative 3x and then go up to our positive 7. 1, 2, 3, 4, 5, 6. I'll put a new mark up there for 7. So that's going to leave us right here, okay? Negative 3 with our x-axis, positive 7 with our y-axis. That's point B. Let's take a look at point C. Point C is at 0, 4. So 0 on our x-axis means we aren't moving to the right or to the left. That means we stay right on, technically, on the y-axis. So we're at 0, positive 4. So we're going to come up 4 points. 1, 2, 3, 4. Our 0, 4 point is point C. Okay, let's take a look at point D. D is at negative 4, negative 1. So we're going to go to the negative 4 on the x-axis and then to our negative 1 on our y-axis. Okay, so that is point D. Point E is at positive 4, negative 3. So we move over 1, 2, 3, 4, and then we come down 3 points. And our positive 4, negative 3 point is right about there. And that is letter E. And our last one is F, which is at negative 3. This time we're at the 0 on the y-axis. So we're going to our negative 3x, but since our y is a 0, we're not going to be going up or down. So our point falls on the x-axis at negative 3, and that's point F. Okay, so that is an overview on plotting our coordinate points on our coordinate axis. The next thing we're going to look at today is symmetry. People enjoy looking at certain objects partly because they have some sort of balance to them, okay? Some geometric figures are more pleasing to look at than others because they too have a special kind of balance, okay? It's called symmetry. Mathematicians give that idea the term symmetry, and it has three different meanings, three different cases, okay? Case number one is a figure symmetrical with respect to a point. Now, the example in the book on page 11 gives you a hexagon, but as I am fairly certain I will be incapable of drawing a symmetrical hexagon, I am going to draw a circle. Not that it's super symmetrical, but I'm a little bit better at it, okay? So, a figure with symmetry to a point means that each point on that figure is the same distance from the point that we're talking about. Okay, I'm talking about the center of this circle. Okay, in the book, they're talking about the center of the hexagon and each point around the hexagon as being equal. Okay. These are all radii of my circle, therefore they are all equal, and therefore it makes this shape symmetrical with respect to this point. Okay, that's case number one. Case two is symmetry with respect to a line. So if we take a look at my triangle here, they have a triangle drawn in the book as well. This is symmetrical with respect to this line, not because every point is equidistant from the line, but because you can draw respective points. Partner points is what they're called. They've labeled this one Q and this one Q sub 1, okay? Their partner points are equidistant from this line, okay? They labeled them all Q, but I'm going to label them something different, okay? And the same here. For every point on this side, there is an equal point on the other side, is basically what we're looking at here, okay? And that is symmetry with respect to a line. The final case is symmetry with respect to a plane, okay? If this is plane X, then this shape is symmetrical to that plane. For every point here on this side of the plane, there is an equal point on the other side of the plane. This point here has a partner point on this side, okay? That makes these shapes symmetrical in respect to this plane. If we take a look at the first three problems of the homework, let's start with problem 1.17. It's asking us the different types of symmetrical means which these figures have, okay? Either a point, a line, a plane, or none. Looking at the letter A, now please just consider my letters to be neatly drawn and actually symmetrical, but we'll have to use our imagination. The book ones are much nicer. But if we look at our letter A, is there any point on our letter A where in which it will have an equal spot on either side? Say if we chose right here, right in the center, right? That would be instinctually where it would go. And at first, sure, we've got a point here and we've got its mirror point here or its partner point, right? And technically, we could partner point here and here as well. But when we come up to this peak here, the vertex of the A, is there a partner point to the opposite side? No, there's not. So we cannot say that the A is symmetrical to any one point. Okay, so then next, let's look at a line. Well, if we drew a line here, would we have equal partner points? No, we would not. So it can't be symmetrical to a line in that direction. But if we take a line and we draw it right down through the center, then for each point, we have a partner point on the opposite side of that line. All right, so yes, it is symmetrical around a line. That being said, if we were just to simply insert a plane into that point, into that line, right? Because a line and a plane are very similar. If we were to insert a plane into this A, it would also be symmetrical around that plane, right? The plane would come out and away from us forever and ever, amen. So it is also symmetrical around a plane. Okay, so A is symmetrical around a line and around a plane if they were both put in just like that. Looking at 118, we've got the letter B, and mine looks terrible. I wrote it 3 times, so this is the best I can do. There is no point where in which B is symmetrical around, okay? But we can, instead of drawing a vertical line, if we drew a horizontal line through our B, we would end up with partner points on both sides of our line of symmetry that would match, okay? So B is symmetrical around a line, and therefore, if it's symmetrical around a line, it is also symmetrical around a plane. They just go together. A plane is just as thin as a line, right? It has no depth or width. It just goes on and on forever, amen. Okay, so now let's look at point, or problem rather, 1.19, the letter C. Again, there is no point. We couldn't put a point here and have mirror points everywhere, because once we got to this point, it just wouldn't work because there's none over here, right? Because they've got to circle the whole thing. But we could, again, draw a line through here. All right, and then here is our point of symmetry. This part here that's empty space doesn't matter so much, because when we're on our line, there's a point here and it has its partner points all the way across equally, and therefore we can say that this letter C is symmetrical around a line and a plane. If we look at number 1.24, for this one, they give us the letter 2. If we look at our letter 2, try to think of where we could put a point of symmetry. A point where every point is equal from that given point. That's not going to work with the number 2. Most of the ones that are equidistant from a point are circular in shape, right? Or hexagonal, that type of thing, where we've got equal distances. That's not going to work with here, with this number 2. So then we have to think of, is there anywhere we could put a line? Could we put a line right here? And could we have points equidistant, or not equidistant, but could we have partner points on either side of that line of symmetry? We couldn't, right? Because here we've got this swoop, and we don't have that here. We don't have, if we drew our line here, if we drew our line here, what if we went with this line? Would we have partner points of symmetry? We don't, right? So for this particular shape, there is no symmetry. So we would write none. There is no line of symmetry, no point of symmetry, no plane of symmetry for this particular problem. All right, let's take a look at number 130. And that asks us to draw all of the lines of symmetry that we can find. Okay, and we're given a rectangle. I've kind of elongated my rectangle. I feel like the one in the book is closely square-like, so it's not as obvious how many lines of symmetry that we can find. But we know that if we slice it down the center, we have lines of symmetry, right? There are partner points for each of these as we move around our rectangle. Okay, if we drew, because this is how rectangles work, we could draw a line of symmetry here, right? And then we have our partner points can bounce back and forth evenly throughout this way. And your next basic instinct would be to draw a line of diagonal, right? But if we do this on a rectangle, do we have actual partner points? Okay, saying that at this level, there should be a point here, and there should be a point here, and here, and here, and here, okay? We don't, so the diagonal for a rectangle anyway, won't work. So when we do our rectangle, we have only 2 lines of symmetry that we can be drawn through our rectangle, okay? So when you're working on the lines of symmetry, perhaps if you have a ruler, a clear ruler, or even a piece of string, if it helps you to see it, to lay it out on the shape or the drawing first, and then it can help you to see what the different lines of symmetry are. Now I'd like to work through part of problem 1.36. In this problem, they have, in your book, they've got 4 different, and I've only done 3, but they've got 4 little coordinate axes for you to use. And they would like to know what would be the partner point to A with symmetry in respect to the y-axis. So here is our point of symmetry for each of these, the y-axis, okay? First thing we want to do to solve this is we're going to plot our A point. And our A point is at -2, 1. So -2 on the x-axis and a positive 1y on the y-axis. And that is our point A. So with respect to our y-axis, what is its partner point? Well, if you think of our y-axis here, we want to see, well, how far away is it from our y-axis? Well, it's 2 points away, right, from our number 1, from our point 1 on our y-axis. So if we stay on our 1 axis, or if we stay at point 1 on our y-axis, and we go 2 points in the other direction, this is going to be our partner point for A. So our A sub 1 point is at 2, 1. Okay, and that is then symmetrical to the y-axis. Let's look at the next one. On the next one, our point is at -3, -3. So we have -3, -3. And this one is done very similar to the one I just completed. This is our point A, and they want the partner point to this. We're going to, and it's still to the y-axis, we're going to remain where we're at on the y-axis, and then we're going to move the same distance away that we are on this side. Well, this side we are 1, 2, 3 points away. So staying here at our -3, we're going 1, 2, 3 points in the other direction. So our partner point, A sub 1, is going to be at a +3, -3. +3 on our x-axis, -3 on our y-axis. Let's do one more. The next one was A is at 4, 2. So a +4 on our x-axis and a +2 on the y-axis. Here's our point A. We want to find the mirror point. We know that this is 4 spaces away from our y. So if we stay at y +2 and we go 4 spaces in the opposite direction, this time negative, it will give us our partner point, or A sub 1. So that A sub 1 is at -4, +2. The last thing we're going to discuss on this video is graphs of algebraic conditions. This starts on page 18, and a graph in a plane is a set of points, and we often use the term graph for a set of points whose coordinates meet certain algebraic conditions. And this graph represented by a drawing in the coordinate plane. Let's look at the graph model 1. So this is model 1, okay, and it is a graph of x equals 3. The graph that would solve this equation or satisfy this equation of x equaling 3 is basically anywhere that x equals 3. So we would simply draw a line anywhere that x equals 3 satisfies this equation. So here is our vertical line. When we have an x equal to something, just a constant, it's always going to be a vertical line. If we have a y equal to a constant, it's going to be a horizontal line. But this is model 1. X equals to a constant. It is every point here that x is equal to 3 satisfies that equation. Model 2 is represented by x plus y equals 2. So the graph is going to be the set of ordered pairs or points such that x plus y equals 2. To graph this, first we want to solve for y. And I know it's counterintuitive. Usually we solve for x, but when we're talking about graphing, we're going to solve for y in this case. So when we solve for y, we have to subtract our x on both sides, and we get the fact that y is equal to negative x plus 2. And then from that point, we can graph this. Let's remember from algebra our graphing techniques here, and I'm just throwing up a quick coordinate axis. Like I said, in your homework, they will have them for you, or you can use graph paper, or you can set them up like this. Either way is fine as long as it's clear so that I can check your work. But remembering from algebra, we know that this is called our point B, okay? And it's plus 2, and it's where our line or our graph of our coordinate planes or our ordered pair solution is going to start. So it starts at plus 2. This is where it crosses the y-axis, okay? So that's our first point. And then we have a negative x. Negative means we're going to have a negative slope. Means we're going from left to right, we should be walking downhill. And since there is no coefficient here other than the 1, we're going to, every point we go over, we're going to go down 1 point. So we're going to go down 1 point and over 1 point. Down 1 point and over 1 point. Then you can take out your handy ruler and connect those points. Now this line represents all of the ordered pairs that are solutions to x plus y equals 2. If this was very clear and we could just pluck one ordered pair out and stick it into this equation, it would equal 2. Okay, that's the point of graphing a line. Model 3 is a representation of an inequality. Still, we want ordered pairs that satisfy this equation, but it's set up a little bit differently. When we graph y is less than or equal to 2, we want to know everywhere that that is equal, therefore it has to be less than. But we're going to start with the y equaling 2 part. Remember what I mentioned before, when we have a y equal to a constant, it's going to be a horizontal line. So here at y is 2, because it's an equals to 2, it's less than or equal to, but the equal is there. We draw a solid line, okay? And now we want every point where y is less than or equal to 2. Well, because we're talking about less than, it's going to go underneath our line, and that is every point. So what we do is we shade it in. Everything under here satisfies this equation. Nothing above the line, but everything below the line satisfies our y being less than or equal to 2. So we shade it in. The final model that we're going to look at, model 4, is represented with negative 4 is less than x, which is less than or equal to 1. Okay, and this model, we're actually going to have 2 lines. First, let's start off with our x is greater than negative 4. X is greater than a constant. So we know that we're going to have a vertical line, and that vertical line is going to be at our negative 4. But because x is greater than 4, or the negative 4, that means it's not equal to negative 4. So the negative 4 is a boundary line. It isn't part of our solution, like here our y was less than or equal to 2. Okay, this negative 4 is not part of our solution. So if you remember from algebra, that means we want to use a dotted line, not a solid line. Solid lines represent that they are part of our solution. Here, that negative 4 is not part of our solution, so we want to make it a dotted line. And then we want all of the x's greater than -4. Now, because we have two lines, I'm not going to shade just yet, but I'm going to draw an arrow to the direction of which I need to shade, right? We want everything greater than -4, okay? So I would be shading this side, but let's finish our equation first because it has another section, right? It has this section here that tells us that x is less than or equal to a +1. Now we know because it's less than or equal to a +1 that the 1 is going to be part of our solution. So we are going to have a solid line drawn there. So at our +1, we're going to put in a solid line because that is part of our solution. And then we want all the x's that are less than or equal to a -1, or a +1, I'm sorry, less than a +1. So we're going to shade that to the left of this line. Now, to shade this one, we want to shade where our spaces overlap. So that means we're going to shade everything between the two lines, okay? Because for this one, we needed to shade to the right. For this one, we need to shade to the left. If this one continued past our one line, then it would no longer fit in this equation. It would no longer be a solution for this equation. We want all the places where x is greater than -4, but also less than or equal to a 1. And that's what is represented here by our shaded region. And that's model 4. One final bit of information to go over is the difference between a union and an intersection. A union is all of the points included from both lines, both equations, right? But an intersection are only the points that are in both of the equations, that are included in both. So we're not going to be, we only want where they're overlapped. So let's take a look at two examples of, or one example of a union and one example of an intersection. The example on page 21, it gives us x equals 3 in union with y greater than or equal to 2. Well, let's do our x equals 3 because we want all of the points included. So to start with our x equals 3, we're going to go to our 3 on the x-axis, and we're just going to draw a line because that is the solution set for x equals 3. It is that line, right? Then we're going to look at our y greater than or equal to 2. Well, because it's equal to, we know the 2 is part of the solution. So we're going to go to our y-axis at 2, and we're going to draw our horizontal line, okay? Because it's greater than or equal to 2, we know that it's going to be shading everything on top of our line, of our y is greater than or equal to 2 line, because everything above it is included. So this is the graphing of a union. We have all of our x equals 3 and our y is greater than or equal to 2. Now, if we look at the same two equations, but this time as an intersection, okay, we want the points that are only in both, okay? And if we look back here were our union. We had all the points included, but this time we want the points that are only in both. Well, if we look here, the points that are only in both are only going to be on this line, because anything off of this line is not x equals 3, okay? And anything below this line here, below our y equals 2, is not in this equation. So for the intersection of these 2 points, we would have to go to x is 3 and y is 2. And then it would simply be a vertical line from that point. This is the intersection of the same 2 equations here, because we only want the points that are in both. And from this point, 3, 2, and vertically up from there, staying on all x is 3, these are the only points that satisfy both of these things together at the same time. And that is an intersection. That completes section 1 of book 1009. If you guys have questions throughout the week, please don't hesitate to give me a call. You've got my information. And then you can do your self-test, sorry, that's in your book, and get those sent to me as soon as you're finished. Otherwise, have a great spring break, and I'll see you next time.